Hello! Welcome to a screencast on chemistry review. Really, it's just chemistry review. All right, so I'm going to share my screen and I'm going to share my iPad. Hopefully, successfully, we'll see. Okay, let me just, figure this out. It's all a learning curve with the technology. Okay, so chemistry review. So chemistry of life really entails two chapters in Campbell biology, chapters 2 and chapters 3. For all of my slides, which I will post on Whipple Hill or on our website, whatever, I will always put down here a link or links to awesome resources. So Mr. Anderson is the man. He runs Bozeman Science, something like that, on YouTube channel. He's on a YouTube channel and he's got AP biology, everything. He's the bomb. I also use the Khan Academy often. I don't like the videos on Khan Academy. I think they're horribly boring. They'll put you right to sleep unless you really need more kind of in-depth information, but their lessons are great and their images are great. I also use Amoeba Sisters and other things. So for chapter 2, it's really the chemical context of life, and you need to know how to read and understand the periodic table. You need to understand the 3 subatomic particles in an atom and their significance, and the types of bonds, how they form, and their relative strengths. So this short video is really going to cover these first 2. So first off, and this should all be a review from chemistry, so we're going to go pretty quick, that atoms are the basic structural units of an element. So if you look at an atom, they are made up of smaller bits. So in the nucleus here at the center, we have protons, which are positively charged. We have neutrons, which are neutrally charged, no charge. And then around the outside orbiting, we have what are called electrons, the smallest negatively charged unit. When I ask you to draw an atom, which I will ask you to do, the way I expect you to draw it is the following. So if we had 6 protons, 6 neutrons, I want you to specify how many of each in a nucleus, right? So 6 protons, 6 neutrons, and then I want you to draw the outer shells. So here's the first shell. That's going to have 2 electrons. And then the second shell is going to have, for this example, 4 electrons. 1, 2, 3, 4. And we just drew the carbon atom, which is really important for all our biological molecules, which we're going to learn very soon, right? So again, number of protons, number of neutrons in a nucleus, and then I want you to show me the electron shells and how many electrons are in them, right? So elements, those are on the periodic table, and they can't be broken down into anything simpler. So if you look at pure gold or pure silver, they are made entirely of either gold atoms or silver atoms. This 96% of living matter is carbon, oxygen, hydrogen, and nitrogen, all right? Of course, there are lots of other things like phosphorus and calcium and sodium and all of those other things that we know are important, but 96% are those things. So what do you think is the most common element in a living organism? And it turns out it actually goes in this order. So 1, 2, 3, and 4, right? So oxygen is the most abundant element in living organisms. All right, so when we look at atoms, as we mentioned before, they are composed of smaller particles. We have positively charged protons, which are in the nucleus. We have neutrons in the nucleus that have no charge, and then we have these electrons orbiting around that nucleus. And again, if we were to draw them, we would draw number of protons, number of neutrons in the nucleus, and then we draw a shell around it and indicate how many electrons, right? So here I just drew a hydrogen atom with 1 proton and 1 electron. So all atoms are electrically neutral, meaning the number of protons are going to be equal to the number of electrons, right? So if you look at any atom, here we have our carbon atom, the number of protons is equal to the number of electrons because they're all equal, right? The number of neutrons is not playing into the charge because they're neutral. All right, and we already drew carbon, so we know that it has 6 protons, 6 neutrons in the nucleus. That first ring, we have 2 electrons. That second ring, we know we're gonna have 4 electrons because we know we have to get up to 6. 1, 2, 3, 4. And you can always go back and check. Number of protons, 6, number of electrons is 1, 2, 3, 4, 5, 6. So when you're looking at anything in the periodic table, you see something like this, right? This little box. And the big number, usually on a corner, is the atomic number. This indicates the number of protons. What else does it indicate? Because atoms are electrically neutral, the atomic number also indicates the number of electrons. Because remember, those are equal in an atom, right? Then this number that usually has a lot of the weird decimals at the end indicates the atomic weight. This is the mass of protons plus neutrons, right? Within the nucleus. So protons plus neutrons. So you have to be able to know those, right? And just to give you a sense of why we use relative mass as like 1 is because the actual mass of these things is so teeny tiny, 10 to the negative 24th or negative 8th. So we just use them as relative, right? So a carbon atom, for example, has 6 neutrons, 6 neutrons and 6 protons. And 6 electrons, actually. But the mass, instead of saying, like we did here, 12, that's much easier than saying this crazy number. All right, so quick. What is boron's atomic number? So we're going to boron here, and the atomic number is 5. What does that tell us about boron? It's going to have 5 protons and 5 electrons. Great. What is nitrogen's atomic weight? So we're going to go over here to nitrogen. Here, we're going to say 14, right? And yes, they can have different numbers down here. I'm not going to get too bogged down in that. And I'm not going to get too bogged down in the rounding. I'll tell you where to round and how much to round to. All right, how many neutrons does nitrogen have, right? So we're going to take the atomic mass and we're going to subtract the number of protons to give you the number of neutrons. All right, draw the subatomic structures of helium. All right, so we're going to deal here with helium. We know that it's going to have 2 protons. How many neutrons? Looking here, we're going to 2 neutrons. That's the nucleus. Then we're going to put a shell around it. And how many electrons? We know that the atomic number is the number of protons, and that also represents the number of electrons. So you have 1, 2 electrons. Great. So when we're talking about atoms, it's important to know that there are isotopes, right? And hopefully you learned this in chemistry. But isotopes are atoms of the same element, but with different numbers of neutrons, right? So let's look at hydrogen first. So here is our normal kind of hydrogen. It has 1 proton. So 1 proton, 0 neutrons, 1 electron. There are different forms of this atom, which is, for example, deuterium, where it has 1 neutron, and tritium, which now has 2 neutrons. The atomic number, meaning the number of protons and the number of electrons, is the same. All right, still 1. However, now the atomic weight has gone up because the number of neutrons has gone up. And here's just another example of having these carbon isotopes. The atomic number is 6. They always have 6 protons. What else does it have? They all have 6 electrons. However, you can see the number of neutrons is changing. Therefore, the atomic weight is changing. Some isotopes, not all of them, but some of them are radioactive. Right? And that radioactivity is caused by, what that means is that these atoms can spontaneously break apart, forming different atoms and releasing energy, right? And these scientists have kind of hijacked radioactive isotopes as a way to conduct certain experiments, right? So here we have the ones that we're going to see in this class are carbon-14, nitrogen-15, and phosphorus-32. Those are all radioactive isotopes that we're going to actually see how scientists use to discover cool things in biology. And some of you may have actually had radioactive testing where you drink a certain liquid that has radioactivity, and then scientists kind of watch how it goes through your body. So that's a good diagnosis. People use it, or doctors use it to diagnose things as well. So some of you may have had that. Okay, so the electron shells in an atom. So electrons always fill the closest shell to the nucleus first. The first shell always has up to 2 electrons. Every other shell after that is going to hold up to 8 electrons. All right. So, for example, sorry, I had to turn the light down a little bit because my computer's almost out of battery. All right, so here we have carbon. Over here, we know it has 6 protons, so we know it has 6 electrons. So that means 2 on the inner and 4 on the outer. Here for oxygen, it has 8 protons, so it's going to have 2 inner, 6 outer, and so on and so forth. If you build up to lots of different shells, each one is going to have 8, up to 8, and that is called the octet rule, which is something you may have learned in chemistry before. Atoms that are non-reactive are called inert, all right? Kind of a weird word, inert. And this means that their outermost shell is completely full. And for the most part, that means it's following the octet rule, and it's full of 8 electrons, all right? So if we look at this example of neon, let's first draw this bad boy. And this is something that I would give on a quiz. So draw neon, all right? So we know that neon has 10, this is gonna be, again, the number of protons and the number of electrons. So we're gonna have 10 protons. This will help us determine the number of neutrons. So we're gonna do 20, I'm gonna round here, minus 10, give you 10. So we have 10 protons, 10 neutrons. Here's my nucleus. Then I'm gonna do the first shell, which has 2 electrons rather. The second shell, we need to get up to 10. We've already used 2, so we're gonna have 8. 1, 2, 3, 4, 5, 6, 7, 8, right? Notice outer shell is full. This is inert. It is non-reactive. It's happy. It doesn't need to do anything. So really quick, rapid fire. Atomic number is 10. Atomic weight is 20. Number of protons, 10. Number of electrons, better be 10 because those are equal. Number of neutrons, 10. Number of electrons in the inner shell is 2. In the outer shell, 8. So atoms form molecules in order to fill their outer shells, to make them happy. So atoms are fundamentally reactive when that outer shell is not full or partially full, right? So oxygen has 6 electrons in its outer shell, right? So if it has 6 electrons in the outer shell, how many are in the inner shell? 2, because the middle one's full. So how many more electrons can it hold, right? So we have 2 in the inner shell. We have 1, 2, 3, 4, 5, 6 in the outer shell, meaning it can hold 1 more here and 1 more here. So it can hold 2 more electrons, right? So biology, and we're going to see this over and over again with our biological molecules, is that carbon is very special, all right? And if we draw that out, we'll see why. I think we already did that, but we'll see anyway. So we have 6 protons, 6 neutrons. Here's the nucleus. Then we have our inner shell with 2 electrons. The outer shell is going to have, we have to get up to this 6 number, so it's going to have 1, 2, 3, 4, right? And what you'll notice is that it has room for 1, 2, 3, 4 more spots. So what that means is that carbon has a huge potential for bonding, right? Lots and lots of potential for bonding. And in fact, because of this, it can make lots of cool structures like rings and chains. And what we're going to see is that it forms the skeleton for all our biological molecules, all right? So what we're going to talk about next time is chemical bonding and how you can get atoms to come together, either atoms of the same or atoms or different kinds of atoms coming together, either through covalent or ionic or hydrogen bonding. All right, so we will stop there and I'll stop the recording. Bye.